Hi, I'm Ed China and I love technology. Now you may have seen me messing around with old cars or strange vehicles, but today I'm in beautiful Trondheim in Norway to find out what this clever machining tool has in common with this huge building in Taipei. Well, to find out we need to learn a bit more about vibration, so check this out.
A vibration is an oscillation around an equilibrium point in a mechanical system. That might sound complicated, but a stringed instrument can demonstrate what that's all about. Energy is built up by stretching the string, and when we release it, what we get is an oscillation, a vibration that decreases if no more energy is added. And we measure the frequency in the unit of hertz. 1 hertz is 1 event or wave per second. There are good vibrations and bad ones. A speaker, for example, would work really badly without vibration. The same is true of an opera singer or an echo sounder. But usually, vibrations are undesirable. They consume energy, generate noise and damage both equipment and people, which is why we use a variety of methods in an attempt to dampen them. Everything from sound dampening all the way up to seismic base isolation systems in large buildings. All objects have what's known as natural frequency, which is the frequency at which the object tends to oscillate when affected by forces like impacts, winds, tremors or imbalance, for example. If the frequency is strong enough and within our hearing range, we'll hear a sound or a noise. In cars, which of course is my specialist field, there are hundreds of different solutions designed to dampen every possible kind of unwanted vibration.
When it comes to machining, it's particularly important that vibrations are kept under control. So I've come here to Sandvik, the leading company in vibration-reducing technology for machining, to see how they do it. And for an engineer and tech nerd like myself, this is nothing less than Shangri-La. So Tormod, can you tell me what are the challenges with vibration when it comes to machining?
If you have a cylindrical tool, approximately 3 times the diameter, that's the maximum length you can go with a solid tool.
Okay.
And if you have a damp tool,
then you can go
much further. The steel has a certain stiffness. Approximately 10 times the diameter, steel has the end. So you cannot go especially further with steel.
So even with the damp tool?
Even with the damper, because the
okay.
stiffness of steel isn't high enough.
Yes.
And then you have to go with carbides, or you have to reinforce it to get it stiff.
Wow, so the carbide is actually the same material that you'd be making the cutting tip out of?
Cutting tip, yes.
So how on earth do you machine that?
That is a big challenge, because it's a really hard material and can only be grinded with something harder. Yeah. And that is diamond. Yeah. Where is the damping bit? Is it sort of all the way through, or is it just at one end? Or? Of course, the vibration is in the front, so you would like to put the damper at the insert. Right. So that would be more efficient. So it's placed as far to the front as possible. Okay. So then the damping magic, if you like, is inside here. So you've got, I can see some O-rings. Yeah, you have to work with 3 things. That is the mass, which is a damping mass, because it's a tuned mass damper. And then you have some springs, because you need to tune to the right frequency. Okay. And then you have something to add damping, which is oil. An oil, actually, so it's very much like a car suspension, where you would have your spring, obviously, to keep your wheel going up and down, whatever, but then also you'd have the oil in the damper itself to absorb that vibration.
Silent Tools uses a damping technique known as tuned mass damping, where a relatively light counterweight inside the tool absorbs kinetic energy of vibrations and uses a compensating frequency to eliminate them mechanically, rather than converting them into noise and heat. Hence the name Silent Tools.
Now Dan, these tools come in all shapes and sizes, I guess, so is this the smallest that you manufacture?
Yeah, this one is the smallest. It's 10 millimeters in diameter and 10 times T in length.
Wow, okay, so that is actually going quite long. Yeah. And you've got all the damping technology in the tip of this, as before. Yeah. That's amazing. That is really crazy. So that is quite one extreme. So what would be the longest tool that you could do?
Yeah, measured in times D. Yep. That's the longest tool we make.
Right, and what is that?
18 times the diameter and 100 millimeters in diameter.
Wow, that is amazing. So, I mean, that really is pretty extreme. I mean, would you say that was the most extreme tool that you do?
Not really, because it's still quite stiff, because it's
100 mil diameter.
Exactly. Well, this one is more extreme and harder to make to work, because it's less diameter and 14 times D.
I mean, obviously in this world of computers and stuff, is an active tool sort of where you're headed, so you know exactly what's going on all the time?
Yeah. The tool over there that we looked at before.
Oh, well, that's it?
That's it.
Wow. Okay, so that's obviously connected up to this machine. So, and that's what the screen is then. So can I try and deflect it? See what happens?
Yeah, you can try and push it.
That sounds like a challenge, but...
Yeah.
Oh, wow, look at that. So what am I managing?
Yeah. So that's 0.4 millimeters.
0.4 millimeters. That sounds... I mean, you know, I'm giving it some. Can we see it actually operate?
Yeah, sure.
I mean, is it like a normal, like a lathe? You'd actually have to set the tool up to make sure it's the right height and the right orientation?
Yeah, that is what the operator will start with, is to look at the tool setup. That's a level, a digital level.
So it knows where it is in space as well?
And we have the live view screen here, which shows
so you've got temperature as well?
Yeah.
Yeah.
So it shows us the deflection and the load of the bar.
Yeah.
Total load is very important to know.
Of course.
And then we also measure the vibration level of the tool, which is very related to the surface you actually get in the end.
Of course.
So these are also two very important features that we measure.
Fire her up, please. Remember the skyscraper at the beginning? Well, it's called Taipei 101 and it's located in Taiwan. And what's interesting is, despite its enormous size difference, it actually uses the same system as Silent Tool's tuned mass damping to counteract vibrations and oscillations brought on by hurricanes and earthquakes. Their counterbalance, however, is slightly bigger, measuring 5.5 meters in diameter and weighing in at 660 tons. It even comes with its own mascot, the Damper Baby. Wouldn't it be cool to make a model to see exactly how tuned mass damping works? Well, I thought so, so I got my friends here at Sandvik to build one. Hi Greta, how's the machining going?
It's going very well. You want to see?
Yes, please, yeah.
Put your glasses on.
Absolutely. Look at that, that's fantastic.
Well, yeah, gorgeous, right?
Well, thank you, Greta. That is wonderful.
There you go.
Thank you. Look at that. I have Greta's part, which is great. So just maybe sand off the edge here.
Yep.
So Karen, should we start attaching this? There we go. I think we're good. Yeah. One more to go.
Nice.
So that's pretty good, pretty good. Right, so now, obviously we have our tower, so there's a small hurricane, or maybe an earthquake. So what would be really good is to actually maybe measure the frequency to see what it is at the moment, because it's obviously going to take a long time to just die down on its own, isn't it?
That's a good idea. So now we have the laser spot here.
Oh yeah, okay, fantastic.
And this is a Doppler laser. So this one measures the velocity.
Oh, that's clever. Okay.
Of this one. So now we can give it a small push.
Okay.
Yeah, and then we just wait.
Yes, obviously that's where Karen caused an earthquake or a little hurricane, and it's coming all the way down and down and down and down and down. It's basically it's taken so long the machine has got bored and just stopped measuring it. So in the same way with the Silent Tool, obviously we now need to have a tuned mass, and then we need to damp it. So what we need now is our little ball, as you say, so our 660,000 kilogram ball down into a little tiny thing, and then we can put that into position.
Yes.
And then once it's in position, we need to tune it, presumably, just to get it
exactly
so it vibrates in relation to the tower.
Because we know we want the frequency of this one and the frequency of the pendulum to be quite similar.
Okay, so let's have a look at our pendulum. Now, what is this weight made of?
This is wolfram or tungsten.
Tungsten, so it actually is very heavy for its size.
Yeah, very high density.
Yeah. Okay, thread it through here.
Yeah.
Really? Just pop that down there for a start. So let's just get it so that it rocks the right way. Is that there, do you think?
Now we can see.
Okay, so it's got quite a fast sort of return.
Yeah.
So now if we lower that down.
I can change the frequency of the ball.
So now if we rock it again. So that's a much more kind of relaxed frequency. So that's more in tune with the ring. So this is exactly effectively what you're doing inside the tools, is you're having to change that or tune that mass so that it actually does this transfer.
Like that.
I think that's quite okay.
Yeah. Oh, that's really interesting. So you can see the energy from the tower being transferred into the pendulum, but then actually transferred back out again.
Yeah.
Excellent. So now the next thing is we need to damp this somehow. So obviously in the silent tools, we use a special liquid, like a viscous liquid, to do that. So presumably we can do this the same sort of way.
So here's
our magic fluid.
Some oil we can use to get some damping into the system.
Probably completely top secret. Excellent.
Basically.
The magic ingredient.
And it will be really interesting to see how this will work. And give it another earthquake, maybe?
Please, yes. One of your finest earthquakes. Oh,
Look at that.
Do that again. So now in a car, obviously the trick with the suspension is basically kind of 1.5 bounces. And just to do that again, you've got kind of 1.5 bounces.
Yeah.
Look at that. That's amazing. Well, that is incredible. So our model tower is now completely resistant to hurricanes and earthquakes thanks to tuned mass damping. And so clearly the physics works whether your tower is nearly 500 metres tall, whether it's a metre tall, or whether it's in a tiny tool.
Yeah.
I think we deserve a little round of applause.
Yeah.
So now you know the similarities between this silent tool and Taipei 101. They're both subject to the same laws of physics and both damp vibrations with the same method, tuned mass damping. Until next time.
More downtime. Another late delivery. Without accurate information, you're not able to act in time. To maintain efficient production, you need to keep track of the process flow, availability, cycle times, and deliveries. Why has machine number 3 stopped again? Knowledge is key. Gathering this data manually takes time, is costly, and you risk losing valuable insights. In the modern workshop, data is collected from connected machines. Machine utilization, stop reasons, and operator input is collected, stored, and made available to you. A real-time visualization of your machine park performance and efficiency. Now, you can take action, in time, based on facts. When subscribing to Coroplast Machining Insights, you get access to your machine data from any device. No hardware installation required. Make use of your data. Increase your productivity today. Explore coroplast.Sandvik Coromont.
In our business, there's a huge competition. If you want to be competitive today, you have to use the latest technology. I'm the owner and CEO of company Riedel CNC.
We are making components for KTM. It's 15D, it's very thin. We need to produce a very large number of these components. It looks simple, but it's difficult to machine.
The chips were long and they were wrapping around the tool and the turret. There were stubs that were not planned before, and this is not good for the productivity.
And we have also broken tools, but we couldn't find a solution with standard ISO tools.
Well, prime turning is something completely different. I knew immediately that this is something for them. I stopped by with Riedel, and we were showing all the videos, all the features of the tool. There we are. We both knew that there is a lot of potential, so we decided to make tests.
Actually, I didn't think that it will work. It was much cleaner. Chips were not wrapping around the turret. They were not stopping the process, and it was much faster. So I thought, that's it. That's the solution.
With pipe turning, we have better stability and higher productivity.
After we start using prime turning tools, we achieved on one single turning machine savings of 1,500 working hours per year on one single machine. Stoppages are down, productivity is up, customers are happy, and so are we.
We're gonna make a guitar that sounds good and obviously gonna be indestructible as well.
We would like to show that steel can actually be very, very strong and light at the same time.
What I really liked about this project is that you put together a lot of different worlds of expertise. And then also we have an end user, which will be one of the world's best guitar players.
We must be able to design and machine a guitar that is unsmashable in all the different ways of how you can smash a guitar.
Well, I got my first guitar when I was 5 years old. And then when I was 7, I saw Jimi Hendrix smashing a guitar on TV. I thought it was cool. It's this silly thing, really, but I thought it was cool. So as soon as I got another guitar, a better one than that, I guess it was about half a year later, I would smash the other one up. And then when I get a better guitar than the second one, I would smash that one up.
Every element had to be drawn from scratch. We're confident that no guitar has ever been built this way before, so my task was to deliver the drawings for the engineers here.
We chose to print the body of the guitar using additive manufacturing, since it makes it possible to produce this kind of design. The material we chose was titanium, since it's a really light and strong material. The benefit is that you can create completely new kinds of designs, which isn't possible with conventional metal cutting today. The remaining powder after the printing will be reused for another print.
It's always a lot more fun to create a guitar for a world-famous guitarist, especially for Yngwie Malmsteen, that is a childhood hero.
The most important thing for me is the neck. It's the most important thing.
The neck is the world's first one made of completely stainless steel. This fretboard is really demanding when it comes to machining because it's so thin.
We are using our highest strength duplex stainless steels together with a unique lightweight structure. So by using this, we have made the strongest and lightest structure ever.
This, what we call a hub, is normally a part of the body. In this case, there's no real joint because we have unified parts of the body together with the neck to have it more rigid. So we are quite certain that this will hold a crash.
No, I mean, I can tell they have a mindset that they want the absolute best result. They would put the work in, put the time in, so on. You know, which I can relate to. I'm like that too.
Of course, this guitar will be beaten a lot more by Yngwie Malmsteen that we can imagine, but I don't think he will succeed smashing this guitar.
So I've been smashing guitar since I was 7 years old. Yeah.
It's utterly unique. It's a showstopper in terms of its eye-catching qualities. And I think a museum would be the right place for it, eventually. Be nice to see.
My style is actually a combination of, you know, playing really loud, a lot of Marshalls and stuff, but more like a violin technique, you know, like Paganini on the guitar.
I'm not going to watch them do it. I'm not going to lie to you. I don't like it.
I hope he will not release the Fury.
It's going to be very challenging. I like a challenge.
Today is the day, and I really look forward to see Yngwie try to smash the guitar. For us, this is really cool to have the whole crowd here to get them look at the guitar that we built together. I think that is a really nice thing.
You have to remember that we are not any guitar makers. This is our first guitar ever.
Well, to break it is impossible, but you can break other things with it.
Really, we managed to create an unsmashable guitar.
I gave everything that I had, 200%. To break this, you're going to hit something that's harder than that. What's harder than that? You know? A ship.
The use of aluminium in the automotive industry has increased significantly in recent years. Poor hull quality, frequent tap breakages and chip evacuation issues are all problems when tapping blind holes. In this film, we will demonstrate proven methods that, when applied, will help meet your customers' demand for efficiency and help reduce the total cost per hole when tapping.
In aluminium cylinder head production, the most commonly used taps are the M6, M8 and M12 series. Many manufacturers use spiral flute taps with radial coolant for through holes and with axial coolant for blind holes. However, this strategy often results in long chips, poor hole quality, and tap breakage. Selecting an appropriate tap with the right flute design is critical to a trouble-free tapping operation. Factors such as core thickness, rake and relief angles, and land width should be carefully considered. In order to maintain tap strength and rigidity, we recommend using a straight flute design with axial coolant for blind holes. This results in shorter chips that can be easily evacuated. Good thread quality and process security can be ensured by using a sharp geometry and maximizing the flute space of the tap. A combination of an optimal substrate and coating gives protection against abrasive and adhesive wear, resulting in longer tool life and better surface quality. To maximize the performance of the tool when high-speed tapping, it is recommended to use a synchronized tapping chuck on CNC machines with synchronized tapping cycles. Oversized threading can be avoided by using a rigid tap holder with microfloat compensation. Thank you for watching. We hope you found this video useful. To learn more about tapping, visit the Sandvik Coromant website.